What's up, everybody? It's Dan from SageMathTutoring.com, and here with a very challenging, I think pretty challenging, calculus problem. And I got a couple problems I'm going to do, I think, for this video. It kind of depends on how much time I have, but let's see. So, geometry student wants to draw a rectangle inscribed in a semicircle of radius 7. If one side must be on the semicircle's diameter, what's the area of the largest rectangle that the student can draw? All right, so I've learned very often, if not always, if you're going to be representing a scenario like this with a diagram, place that semicircle sort of here in the center, almost as though it was like a regular circle, but it's just a semicircle. Okay, so we're only really focused on this top green half here. Now, the reality is we're putting a rectangle inside of this like that. All right, and we want to find out what's the largest area this rectangle can be. Now, sort of the constraints here are such that the radius is 7, so I think everyone understands that the point here would be 7 comma 0, the point here would be negative 7 comma 0, and the point here would be 0 comma 7. And I'm going to say that let's make this little piece X, this little piece here. So there's sort of X distance away from the origin, and this piece right here we could call Y. So if we were to think of this little piece as X and this entire sort of height of the rectangle as Y, well, I think everyone can see, well, there'd also be an X over here. So we're dealing with a rectangle that ultimately has this 2x down here and a y here, okay? Now, therefore, the area of this is, of course, length times width, but we know that that is going to be 2x times y. Now, you might be wondering, what am I doing? Well, what I'm doing is I'm immediately thinking of what equations are probably going to come into play. They're asking me what the area of the largest rectangle that could be drawn is. Well, clearly the area formula seems very relevant. In fact, my student who's watching knows we're going to be taking the derivative of this formula, because that's what you do with optimization problems is you take the derivative of the formula, the special formula you need, and then you set that equal to 0, and then you like solve for a variable basically, right? Um, but the problem is we have two variables here, and that's where we need to bring in yet another equation that would somehow relate x to y. And I think my student watching knows that that most definitely would be the equation of the semicircle. Now let's be very clear, the equation of what would have been the full circle, that most definitely would have been x squared plus y squared plus equals radius squared. And we know that the radius is 7. So that's going to be 7 squared, also known as 49. However, we are dealing with a semicircle. So often when you're dealing with a semicircle, what you want to do is you actually want to solve for y in a sense. And of course, you could do that by subtracting x squared from both sides. You have y squared equals 49 minus x squared. You could then take the square root of both sides, and then you would have this square root of 49 minus x squared. Now, at this point, you might be wondering, well, aren't I supposed to do a plus minus here? If I'm doing the square root of both sides here, shouldn't I have done this plus minus thing? Well, I would say, yeah, typically you do. However, remember, we're only dealing with this top half of the circle. In other words, we're only dealing with the positive y values here, the positive y values, which means we only need to put a plus here, right? Because we're only dealing with positive y values. So therefore, we do not need to put a plus minus here. So this is the equation of the semicircle. In other words, anytime we see a y, we can replace it with this radical 49 minus x squared. So that is exactly what I'm going to be doing. I'm going to be replacing that y with this, radical 49 minus x squared thing. Okay, I'll even keep it color coded. All right, so this is the beautiful area equation that now features only a single variable that we can now deal with. And therefore we should take the derivative of this. Okay, now let's look at this. It's going to be a product rule. How do I know? Because I have an x times this other sort of function that features x, so this is a product situation. Now let's be very clear. Product rule says if you have an original equation called u times v, the product rule says that it's u prime times v plus u times v prime. And we know that the u is, we could say x, and we know that the v is the radical. And in fact, let's call the u 2x. We'll group this. We'll call the u 2x. Now, why am I doing that? I'm doing that because we are going to employ this structure soon, but I'm sort of a fan of going off to the side and just writing down the cast of characters. The u is going to be 2x, and the v is going to be this radical 49 minus x squared. But let's be clear, that's just 49 minus x squared to the 1/2, right? To the 1/2. We'll bring this over here, and we'll save it for later. So shrinking it down a bit. Focusing on this. Now we have u prime. I think everyone understands that's clearly going to be a 2. V prime, this one's going to be a chain rule scenario. It's a power rule, but a chain rule version of a power rule. So 1/2 times 49 minus x squared to the negative 1/2, but then we have to hit it with the derivative of 49 minus x squared, and that will be negative 2x. Hopefully that makes sense to my student watching. Let's clean that up a little bit. And that would most definitely be a scenario where this 2 cancels with that 2 for sure. It's also a scenario where this thing kind of goes to the denominator. And what's left up top? A negative x is left up top. So we have a negative x all over, and let's turn it back into a square root. It would be the square root of 49 minus x squared. So what have we learned? We have learned that v prime is that. Okay, so now we're ready to adhere to this structure. Okay, so let's say a prime is equal to, it's going to be u prime. Well, we already know what u prime is. It's 2. It's going to be equal to 2 times whatever v was. V was this thing. I'll leave it in square root form, however. So it's going to be the square root of 49 minus x squared. And then it's going to be plus u, whatever u was 2x. I'll put it in parentheses, times whatever v prime is. Now, v prime we made clear is this thing. So we have a negative x up top all over radical 49 minus x squared. Okay. Now, cleaning it up a bit, we have 2 times radical 49 minus x squared minus 2x squared all over radical 49 minus x squared. So that is a prime. Now, everyone knows we must set that equal to 0. So therefore, this whole thing is going to be equal to 0, but here's the deal. This denominator is terrible. Let's get rid of it right away. How do we do that? By multiplying literally everything by the denominator. We're going to multiply this by the annoying denominator, 49 minus x squared. But we're also going to multiply this by radical 49 minus x squared, and we're going to multiply this by radical 49 minus x squared. As a result of that, of course, this becomes a 0. Over here, we have 2 times. Now think about it. The square root of something times the square root of something is just whatever was in the radicand. So in other words, we cancel the square root symbol, but we leave behind 49 minus x squared. Now I think everyone understands these will cancel. In fact, that was the point of this whole thing. So we have minus 2x squared. So now, distributing the 2, we have 98 minus 2x squared minus yet another 2x squared. Now, we have therefore a 98 minus 4x squared. Adding 4x squared to both sides gives me 4x squared equals 98. Dividing both sides by 4. 98 over 4. I don't know what that is. However, let's do the square root of both sides right now. Okay, we're going to do the square root of both sides. And we don't need to deal with the negative version because it wouldn't make sense to have a negative x in this context. So we would have x equals radical 98 over 2. All right, now that is a nasty number, but we're going to have faith. We're going to have faith that that is the proper x. Now let's remind ourselves. Remember back in the day, back forever ago, we knew that the area was 2 times x times y, and then we sort of replaced the y with this blue guy. Well, let's just bring it down because we know that that still applies, right? I mean, the area is most definitely this, right? This formula, okay? Now, let's be brave and plug in uh, radical 98 over 2 for x, because remember, that is what they're asking for. Okay, let's remind ourselves, what's the area of the largest rectangle that student could draw? Well, we found the x value that corresponds with that optimized area, so therefore, let's go ahead and plug it in. 2 times radical 98 over 2. We'll deal with that in a moment. We have 49 minus something squared. What's the thing that's going to be squared? Well, it's going to be radical 98 over 2. Okay, these cancel. Next thing you know, you have a radical 98 times radical 49 minus, you ready for it? This gets applied to the top and the bottom, doesn't it? When it gets applied to the top, it becomes a 98. When it gets applied to the bottom, it becomes a 4. All right, so we have radical 98 times radical. Let's get a common denominator going. 49 times 4 is 196. So we would have 196 over 4 minus 98 over 4. So therefore, we have a radical 98 times something over 4. Well, it would be 196 minus 98, and it turns out that that actually is 98. Okay, isn't this awesome? Okay, so hopefully we're all remembering the laws of radicals such that you could split this one thusly. I think we all understand, therefore, that this would be radical 98 times yet another radical 98 over a 2. And then we could remember, oh, there's a 1 here. So then we could be like, okay, cool. Radical 98 squared over 2. Okay, this squaring action cancels the radical, leaving us with a 98 over 2. All right, what is that? 49. That's the answer. Good Lord. Good Lord. For my student watching, yeah, is the teacher going to give that on the test? I don't know. I do not know. But yeah, pretty crazy, but that is how you do that one. Now, for my student watching, we had attempted this before. I think where I went wrong with my student before was I was trying to come up with some value for that when I really should have just recognized that we could call this part x and therefore the entire length is 2x. I think there's no question that the height of the rectangle should be y. Um, notice again for my student watching, we didn't have to say minus 7 minus x or some, we didn't have to say something minus something else. We could be very straightforward. This is just 2x. Okay, let me do another problem. A rancher wants to construct 2 identical rectangular corrals using 500 feet of fencing. The rancher decides to build them adjacent to each other so that they share fencing on one side. What dimensions should the rancher use to construct each corral so that together they will enclose the largest possible area? 500 feet of fencing, building them adjacent to each other. Yeah, so whatever, we'll just imagine it's this, right? We could call this X, we could call this X, we could call this Y, Y, Y. This is X, this is X. For my student watching, I think my student recognizes probably that the total area of this is going to be 2x times y. That looks familiar actually. And we also know that the all the sort of x's and y's, if you were to add it all up together, well, that's going to add up to 500 feet, right? That's going to add up to 500 feet. So that would be another equation that we could sort of take into account. We know that 500 it's going to be, well, what would it be? It would be four total x's added together and, adding that to three y's, right? And at the end of the day, we are optimizing area, so we are going to want to take the derivative of this. Let's just make a decision right now that it would be, maybe we could just replace the y again. Let's actually keep it similar to what we did in the last problem. So in order to do that, you would have to sort of solve for y over here. I think my student watching understands that's nothing more than subtracting 4x from both sides and then dividing by 3 ultimately. So we have 500 minus 4x all over 3. Now that is kind of nasty, but whatever. We then do the special move of updating this. Notice how we're not doing the derivative yet, right? So for my student watching, just know you shouldn't do the derivative yet because you still have two variables. I'd say probably with related rate problems, it's going to be the same thing. Like don't hit it with the derivative until you only have one variable over here if you can help it. Okay. I don't know if there are exceptions to that. There might be exceptions, but I would say for the most part, if you could just make it so there's only one variable here before you hit the derivative, make it so that there's only one variable. So I think my student watching understands. We, of course, will be putting this here. Can we clean it up a little bit? Well, probably. I mean, my first instinct, I don't know if this is dumb or not, but is to take that sort of 3 out and then realize that we're dealing with this. Would it make sense for me to just go ahead and distribute? I think so. Yeah, it's sort of unavoidably annoying, but I mean, we are looking at, 1,000 over 3x minus 8 over 3x squared. Yeah, not the most fun, but I think I'd rather deal with this than anything else because we could just do the power rule with all of this. Okay, now it's time to do the derivative. So we have this, and we have minus 16 over 3x, which is really not that bad. Setting that equal to 0, we have this. Now we can multiply everything by 3, which is awesome. So we have 0 equals 1,000 minus 16x. 16x equals 1,000. X equals 500 over 8, aka 250 over 4, aka something else. So 1,000 divided by 16 is 62.5, and that's really 1,000 divided by 16 is, like I said, 62.5. So that's 125 over 2. Okay, so that's 125 over 2. So each of these x's is 125 over 2. They're asking what dimensions should the rancher use to construct each corral. So to construct each corral. So this is one of the corrals, so the dimension here is 125 over 2. We also need to know what this one is. Now, we already knew that y is equal to 500 minus 4x over 3. So let's bring that down, and that's going to give us the other dimension. So plugging it in, 500 minus 4 times 125 over 2 all over 3. This would turn into a 2. 500 minus 2 times 125, which is 250, all over 3. That is 250 over 3. And that's going to be y. So remember, y was equal to this. So y is equal to that. So therefore, these x's are each 125 over 2, and that's 250 over 3. All right, kind of tricky. I mean, obviously, you should definitely draw a diagram. I mean, that's for sure. All right, let's keep going. A company has started selling a new type of smartphone at the price of 140. This, where X is the number of smartphones manufactured per day. The parts for each smartphone cost $60, and the labor and overhead for running the plant is $7,000 per day. How many smartphones should the company manufacture and sell per day to maximize profit? Well, they're bringing up profit. Obviously, we're going to need a profit formula or equation, and then we could do the derivative of that. But it's good to remember profit is equal to revenue minus the cost of doing business. Now, revenue is how much money you're bringing in. And revenue, you could say, is the price of a product times how many you sell. So already we have this sort of thing and this sort of thing to deal with. Now, this is the king formula. The price is this. Okay. The parts are 60, the labor is that. So this has to do with cost. Okay, it's saying how many smartphones should the company manufacture and sell. So it's assumed that these will be the same quantity. So the amount manufactured will indeed be the amount sold. So let's be very clear. Revenue is going to be the price. Now the price was given here. So that's going to be 140 minus 0.05x times the amount that you sell. Well, x represents the number of smartphones manufactured per day, but we already made it clear that the number manufactured per day are going to also be the number sold per day. So therefore, how many are we selling per day? Well, that's also going to be x. Now, the cost of doing business is going to be 7,000 no matter what, plus $60 times however many smartphones you're manufacturing. So that's going to be 7,000 plus 60x. So therefore, to update this equation, we could say profit, also known as P of x, is equal to, this thing, revenue, minus the entire quantity of this. And we can certainly clean that up. So this would be 140x minus 0.05x squared minus 7,000 minus 60x. And that becomes negative 0.05x squared plus 80x minus 7,000. So that, of course, is profit. Now we can go ahead and take the derivative of this. Of course, we'll be setting it equal to 0 soon. So we have negative 0.1x plus 80. We get set that equal to 0, and that becomes this. Let's multiply everything by 10. Multiply everything by 10, and that would give us 0 equals x plus 800, negative x, pardon me, and then x equals 800. So that's the answer. A graphic designer is asked to create a movie poster with 162 inches squared photo surrounded by a 2-inch border at the top and bottom and a 1-inch border on each side. What overall dimensions for the poster should the designer choose to use the least amount of paper? Well, let's draw it. So we have a 162 square inch photo, 2-inch border at the top and bottom. Okay, here's the photo. And here's the border on the top and bottom, which is a little thicker. Overall dimensions for the poster, should the designer choose to use the least amount of paper? Let's call this X, we'll call this Y. I think my student watching knows that this is going to be X plus 2, and this right here is going to be Y plus 4. Now the reason for that is because this is a 2-inch thing, so therefore it's Y plus 2 plus this 2, giving me the entire Y plus 4. I think my student watching probably understands that's 1 inch, that's 1 inch. So that's going to be x plus 1, giving me x plus 2. Now, we know that the area of the whole poster is most definitely going to be, x plus 2 times y plus 4. But we have two variables. We would, of course, take the derivative of this, set it equal to 0, and then solve for some variable. But we have two variables. So, rule of thumb, try to make it so that there's only one variable. And the other equation we could take into account is the fact that we know x times y. We don't know what x is, we don't know what y is, but we know that when we multiply them together, you're going to get 162. Let's solve for y. That would be 162 over x, so therefore we can update this equation to say x plus 2 times 162 over x plus 4. Now we can FOIL it. First times first would give us 162. Outer times outer would give us 4x. Inner times inner would give us something over x. 2 times 162 happens to be, drum roll, 2 times 162, 324. Last times last gives me an 8. So we have that. Derivative time. Well, before we do derivative, let's remember that this could be rewritten as x to the negative 1, which is going to be helpful. And also, let's simplify, right? So we have 4x plus 324 x to the negative 1 plus 170. Now we're ready to do the derivative, and that would be 4 minus 3 to 4x to the negative 2 plus 0, so we don't need to worry about that. I think my student watching understands that that would be cleaned up as this. And also, let's get it over with. We can set it equal to 0. Let's add 3 to 4 over x squared to the other side. Now, what I like to do whenever I have a variable like this on the bottom, and it's a single fraction and a monomial over here, is I just swap these. Now, that's really nothing more than multiplying both sides by x squared divided by 4. But you could do the little swap-arino, and then we have this. Now, square root of both sides would give us, only focusing on the positive, square root of 324 over the square root of 4, which is 18 over 2, believe it or not. And then that's going to be x equals 9. Okay. So to be clear, we took the square root of both sides, and we only considered the positive version because it would not make sense to have a negative x value in this context. So what overall dimensions for the poster should the designer use? Well, if x is 9, then this is 11. If x is 9 here, then this would be 22 if you were to work that out. All right, 162 divided by 9 is 18. 18 plus 4 is 22. So that's the answer to that one, 11 by 22. Which point on the graph of y, blah, 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 is closest to the point 1, comma 0? Well, here's the graph of y equals radical x. 1, comma 0, that's this. Well, we want the shortest distance between this point and some point here. So we're minimizing the distance. Now that implies distance formula. So the coordinates of this green point would be x, and believe it or not, the y coordinate would be radical x. How do I know that? Because every y coordinate on this curve could be represented as radical x. So that's the insight you need for this one. And let's remind ourselves the distance formula is, x2 minus x1, y2 minus y1. Let's go ahead and call this x1, y1. We'll call this x2, y2. So when you fill that in, you are therefore dealing with 1 minus x squared plus 0 minus radical x squared. Cleaning that up gives you, well, foiling the first thing would be 1 minus 2x plus x squared. And that would be adding this negative radical x squared. Now the negative would cancel because negative times negative is positive, and the square root symbol would cancel as well. So we would end up with just an x there. So let's clean this up further. It would be x squared minus x plus 1. And let's also remind ourselves that that is x squared minus x plus 1 raised to the 1/2. Now we're ready to do the derivative, and that would be 1/2 times the same thing. But this would be minus 1/2. Now this is a chain rule scenario, so you now have to multiply it by the derivative of what's inside the parentheses, which is 2x minus 1. Cleaning that up would give us the 2x minus 1 up top, then you'd have 2 times a radical down below, x squared minus x plus 1 in there. Setting this equal to 0 means we could kind of ignore that now, because if you multiply both sides by it, then it would go away. So you'd have 0 equals 2x minus 1, adding 1 to both sides, and then divided by 2. So x would be 1/2. Now, if x is 1/2, well, that corresponds with this x, but the y is going to be radical 1/2. Now, if the teacher is a stickler for rationalizing the denominator, that would become 1/2 comma radical 2 over 2. In case it's not clear why, just remember this could be represented as this, which could be represented as this, which could then be rationalized, and that would give us this, which is what I wrote here. So that is the answer to that one.